In Hirsch's papers, he talks a lot about something he calls the Hole-electron asymmetry in condensed matter. And he has one paper, which has a link here, or you can link to it on your phone there, where he actually qualitatively describes in a pretty nice way what he means by the Hole-electron asymmetry of condensed matter. Normally when you're doing condensed matter physics, you can talk about electrons, which are negatively charged particles, or holes. And holes are interpreted by a lot of people to mean the absence of an electron, so it would be a positive charge where an electron could have been. And they talk about them fairly symmetrically. So they say, for example, that an electron current moving to the right in this picture is the same as a hole current moving to the left. And almost all their equations work out great, because when you change the sign of the charge on the charge carrier, the negative electron versus the positive hole, you also change the direction of the velocity. And so things like the sign of your current actually stay the same, and this is what Hirsch describes as a symmetry. So you can't tell the difference between holes and electrons in most condensed matter physics. When you get to superconductors, this is where Hirsch points out the Hole-electron asymmetry. And in superconductors, there are experiments that show that the particles involved have to be electrons and can't be holes. One of those is the experiment that shows the London moment. And what happens in that experiment is they physically rotate a superconductor, so say our superconducting cylinder here, and a magnetic field is created that points up out of the superconductor if it's rotating in a counterclockwise direction. And that field points up because the charge carriers creating the magnetic field are electrons, or negative charge carriers. If the charge carriers creating electrons were holes, they would be positive and the magnetic field would point in the opposite direction. So what Hirsch means when he says the Hole-electron asymmetry in condensed matter physics is that in superconducting materials there are experiments where you can tell that the current involved is a current of electrons and not a current of holes moving in the opposite direction. Which brings up direction, and the reason we believe that it's electrons is we believe the charge carriers are actually moving a little bit behind, but mostly along with the rotating superconducting cylinder. And so electrons spin this way with this superconducting cylinder, and we get a magnetic field up this way, parallel to the velocity, the rotational velocity vector actually. Parallel to the rotational velocity vector actually. Now Hirsch goes on to show this mathematically in his article, and what he does there is starts with the equation for this for the London field, or this magnetic field I talked about in the last slide. And the equation is that the curl of the velocity of the superconducting carriers is equal to the negative of the charge of the carrier over the mass of the carrier times the speed of light times the magnetic field that's created. And Hirsch takes that and says that you can actually derive the penetration depth of the superconductor using this field. The penetration depth of a superconductor is how far a magnetic field can penetrate into a superconductor before it's shielded out. To do this, Hirsch uses the equations for current density, Maxwell's Faraday equation, which says that the curl of the magnetic field is equal to the current density that created it, and a vector identity that says the curl of a vector field is equal to the Laplacian of the same vector field. And what we want to keep in mind is that the rotational velocity field, or the velocity of the superconducting charge carriers, is equal to the angular velocity cross producted with the radius that the charge carrier is out along the cylinder. So Hirsch shows how to do the derivation, and then he comes back and says, okay, what about this derivation can tell us that we can't substitute holes for electrons? And he says, well, this first step doesn't. The first step, if I put a hole in here, that's going to change the negative sign here, and this is actually a typo that needs to be corrected. and it's also going to put a negative sign in front of my velocity, and so those two negative signs would cancel and I'd be right back where I started. So okay, so that's not it. The penetration depth equation itself doesn't tell us anything because the charge is squared, and so if I try to change the sign of the charge, I'm going to wind back up. -1 times -1 is 1, and I wind up back where I started, so that's not it. The thing that tells us we can't change anything is that whereas this equation is true, that the hole velocity is equal to negative the electron velocity, with relative to the crystal lattice that they're sitting in. So in other words, that equation is true if the crystal lattice isn't moving and we're trying to talk about electrons or holes moving relative to the crystal lattice. However, that equation isn't true for this kind of motion where the electrons and or holes, whichever one they are moving along with the crystal lattice for the most part. So he says since that's not true, then if I change the sign here, that actually implies that I've changed my direction of rotation, which I haven't. The next place I would have to look would be to say that I changed the direction of my magnetic field. But I can't. I actually measured the magnetic field, and I know that it's pointing up here. So what that leaves me with is that there's an asymmetry. I can't substitute an electron for a hole in this case. It has to be electrons that are circulating along with the superconductor to make this London magnetic field. So that's the picture version and the mathematical version of Hirsch. If you really want to dig in, the way Hirsch derives the penetration depth from the velocity and the London magnetic field is shown here as a backup slide. The curl of velocity field is equal to the negative of the magnetic field with some constants sprinkled out in front. We saw that before. This is the current density, which is equal to the density of superconducting carriers times the charge of an electron times the velocity of the carriers. This is Maxwell's Faraday equation, which is curl of the magnetic field is equal to a few constants in front of the current density that created it. And then what we do is we take the curl of both sides of this equation. So that gives us del cross V sub s. And on this side, the curl of B is equal to 4 pi over C times J sub s, but J sub s is equal to N sub s, E sub s, V sub s. So there's J sub s, N sub s, E sub s, V sub s. Here's our constants that were there before we substituted for B. And this is a V sub s that is a typo. It should not be there. Anyway, and what that all equals is negative 4 pi N sub s, E sub s squared over C squared ms squared. Now that's kind of promising because that is actually the inverse of the penetration depth squared. Then we use our vector identity and we say negative del cross V is actually equal to del squared V. And that's just a differential equation that looks like this. So we have del squared V equals 1 over lambda squared V sub s. And the solution to that differential equation is that V sub s is equal to e to the negative position r over lambda, plus or minus a few constants wiggling around somewhere. And what we see is that the exponential decay rate for the velocity field is lambda, and so that's the same as the penetration depth. And if you look at how this is written, 1 over lambda squared, that's going to be this number here. And like I said earlier, that number is 1 over the square of this number, 1 over lambda squared. And so that's how you derive it when and if you need to as a backup slide.